fact, if you've watched the show before, you know that we love chatting cutting edge when it comes to PC hardware. And it doesn't get any more cutting edge than Intel's Optane technology.
Yes, and here to tell us about Optane are Avi and Mathew from Intel. Welcome, guys.
Good morning. Thank you for having us.
Yeah, so just to set the stage for everybody, give us a little background on what you do at Intel.
Sure. So I'm Avi. So I joined Intel 10 years ago. I'm back in Southern California. Went to school at USC, fight on. And been with the Intel storage team for the past 10 years. Have had my stint in design engineering, design validation, and now I do product line manager for all the Intel client Optane products.
Excellent.
Cool. Mathew?
Yes, I'm Mathew, currently a marketing engineer with Intel. I've been working on the Optane technologies for about 2.5 years now. My past lives have involved being in the Air Force as a cryptological linguist and doing computer sales.
Awesome.
Right on. And so, I mean, you were saying you've been with Optane for a couple of years. How did you guys kind of find your way into this segment at Intel, focusing on the Optane tech?
So within Intel, we have a storage group called NVM Solutions Group, where we make NAND SSDs, as well as the recently launched 760. I believe it's available on your websites as well. And we have another group within the organization which concentrates on new memory technologies. Mm-hmm. So we've always made NAND and NAND components and NAND SSDs, but in parallel we've always looked for pushing the envelope on memory technologies, and that's how Optane is not a year program or a 2-year program. It's been
something in development for a little while.
It's been in development for years, and last April is where we first introduced Intel Optane memory, mm-hmm. which uses 3D Crosspoint. 3D Crosspoint is just the memory component. Mm-hmm. Think of it as equivalent to NAND. Optane is our Intel's brand of products, which use 3D Crosspoint in its in the SSD. We have data center products, client products, and within client, Optane memory, Optane SSD, 900p, which was launched late last year, and 800p, which we're launching today.
Oh, fantastic. And so, to expand a little bit, when you're talking about 3D Crosspoint, I think a good chunk of our audience is probably familiar with Optane. But can you expand just a little bit more on what makes Optane different from a technology perspective? We're throwing out words like NAND and 3D Crosspoint, and mm-hmm. For someone who might not be familiar with what you're trying to achieve with that, how do you separate the two? What makes Optane special?
And feel free. I know you guys brought some slides, so feel free to refer to those.
Yeah, if you want to jump in on something like that.
Oh, maybe there's one slide here which I'll just use as a reference. But fundamentally, right? If you asked any engineer what's the best memory technology, mm-hmm. What everyone is trying to go achieve is, first of all, it to be non-volatile. Mm-hmm. Meaning, when you power off, the data needs to reside, unlike DRAM, which is a volatile technology.
Right.
And secondly, you're trying to go and get the latency, define latency by how quickly can I access anything from the storage media to ensure that the process which is coming from the host is satisfied.
Right.
And the latency and non-volatility is what makes 3D Crosspoint different compared to a NAND. And along with that, we have high-end endurance. These memory technology, 3D Crosspoint is extremely high enduring. Mm-hmm. You can read and write to it much longer and much more.
Sort of satisfying some of the fears that we had with early SSDs. Yep. This read-write cycle. Mm-hmm. Yep. I think there was a lot of nervousness when SSD started making it to consumers. Like, oh, my data is just going to evaporate, or I'm going to exhaust all of my read cycles. And I still have like my old first-gen SSD, which it's probably not doing great, but
the NAND technology basically relies on a concept of trapping electrons. It's containing data, and it's kind of a finite proposition. You can only keep it in place for so long, and especially mm-hmm. the earlier technologies, when we were first figuring out how to trap microscopic components of an element. There was obviously a lot of learning and a lot of challenge there, but 3D Crosspoint, the underpinning media here, does not have that same type of
like
functional implementation.
I was going to say degradation concerns or anything like that.
Well, that and it's a little more dynamic. It's less static. We don't necessarily have to go through this system of trapping everything in one and then containing it in a given state. We can change things on a much smaller scale, and we can do it much more dynamically, giving us the improved latency and then also the improved endurance, because we don't have to go through and change the state of it so often, or we can change it where it is. We don't have to move it somewhere else in a change state, the read, modify, write.
Again,
no garbage collection. No,
I was going to say it's a little less of those fears that we have with like trim and getting into
doesn't
sorting like
relevant.
that. Yeah.
Yep.
Now, people talk about Optane making your computer feel faster.
Oh, yeah.
And in terms of system acceleration and responsiveness, how does Optane do that?
Trisha, going back to my comment about latency, Optane, because of the 3D crosspoint memory media, our SSDs and memory solutions are able to achieve a latency of, much less compared to a NAND. A typical NAND SSD, you're talking about latency in the order of 90 to 100 microseconds, wherein with Optane, we're talking less than 10. And that latency benefit can be realized in multiple areas in a client PC workload. You boot, means your boot's faster.
Yep.
You
I've been waiting for tens of microseconds. What's going on? Come on.
Table flip.
Yeah. So all of those, right? So it's everything you do is going to be much responsive, and that's because the Optane is able to deliver the data back to the host at a much quicker rate compared to a NAND solution.
Well, another side to this, and this is going to come up when we talk about the random read performance or the IOPS that we have on these the laptops currently, is it has to do with the scale at which we can retrieve that information.
Okay.
So the fastest memory in the machine is typically DRAM. You can basically fetch. And I'm just using analogies here, but you could fetch like a word at will. You just say, I want this one word. With NAND, it's more like you're fetching, a chapter, and then you need to find that word that you wanted.
Gotcha.
So you're grabbing a huge amount of data, because that's kind of the size, the minimum resolution at which you can retrieve it. And with Optane, we're closer to something like a sentence. So it's not quite as fast as the DRAM is yet, but it's far tighter than NAND is. So when you're going through all of these application launches, when you're loading your enemies in a game level, what have you, those are all little pieces of information. So with NAND, when you have to go through and grab a giant chunk of information to pull out the little bit,
It's a little more wasteful.
It's a lot less efficient. So a lot of that delay is basically it trying to filter through much larger amount of information to pick out what you actually wanted.
Well, and so getting into some of those applications, obviously Intel has numerous markets in mind for different styles of Optane. What are some of the target markets, and what products kind of line up with, Optane for consumers versus Optane for businesses? Where does Intel see the sort of the fit for some of this technology?
Sure. So we have 3 products with the introduction of 800p, which will be available for all the customers and consumers to buy. One is Optane Memory. So think of Optane Memory as traditional hard drives are slow. You take Optane Memory as an accelerator, put it in front, and you still keep your hard drive capacity, and along with our Intel software, which is the Intel RST, which does the acceleration for you. It moves all your critical files over to the Optane, and thus giving the end user responsiveness of an Optane.
Nice.
But lets them also keep the density, like your 1 terabyte or 2 terabytes of your hard drive. That's caching. We don't like to call it caching because we do a lot. The reason is we do a lot more.
Can you turn it into a verb? Can you say we're obtaining? Is that?
I'm sure my PR and legal guys are watching.
Don't put a lot of pressure behind it. It's not the best.
No,
idea.
but the reason I say it's not caching is traditional caching just as block, LBA, kind of caching, wherein with Optane, our software also does something like file. So it's more file aware from a system standpoint. It tracks your behavior, and so if you opened a Photoshop application or a Chrome browser, it knows that there is a recency effect to it. So meaning it knows that you're opening these applications on a pretty regular basis. So as a result, it's important for you. So let me move over to the
Intel
Optane.
software is really looking at the consumer behavior.
Yes.
So the whole reason we put off the caching is just because it's too generalized. There's a million different ways you could implement something and then call it caching, and we don't want to fall into this the broadest and simplest category of caching, because what we do is so much more advanced than that.
Right.
As Avi was saying, for example, it may be looking at the recency with which files were accessed, but it may also be looking at predictively, like if these files were being used, then these files may also be used, or looking at a lot of different potential use cases, but also, it's just far more complicated.
You're getting better. It's like, it's just better.
It's just better. So say I want to make that better Optane upgrade. What would I need to have in my PC from a hardware compatibility standpoint to make that upgrade?
Yeah, I'm sure, because we like to talk about system building holistically. I'm sure just throwing Optane into my old Franken build, probably I wouldn't be maximizing the benefit of what you guys are trying to bring to the table.
As long as it was at least a 7th gen desktop, like the Z270s.
It's okay.
No.
It's okay, bud.
I mean,
So for Intel
you
Optane,
can just twist the knife.
for Intel Optane memory, just look for the badge which says Intel Optane memory ready.
Okay.
So we have more than 350 motherboards, where we worked closely with all our OEMs to make sure the system's ready for Optane memory. It's a M.2 socket, and on the box, if it says Intel Optane memory ready, which is starting 7th gen, and now all the 8th gen boards are supporting.
Great.
It's just plug and play. And for 800p, no such requirements. It's any board which supports PCIe. So what we have here with the 800p is it's an M.2, pretty standard form factor. And we wanted to, that's again, one of the reasons with Optane is we wanted to make sure the enablement was easy. So we brought it in form factors which were consumable and didn't require wholesale board changes. This product is plug and play, any PCIe supported platform will,
PCIe, NVMe.
Nice.
Awesome.
And so especially because you guys are trying to change some of this discussion on, I mean, like, the hoops we have to jump to sort of define caching and why this isn't caching. How are we taking a look at the performance metrics? How does this change benchmarking for a storage solution? Like, what numbers become relevant when someone's trying to say, like, is this an upgrade that makes sense for me?
Yeah, if you ask Intel, random is what matters. Random IOPS is what defines performance from a storage standpoint. Traditionally storage was divvied up into sequential read, sequential write, random read, random write, because the metric was all the storage technologies at that point were not able to provide one metric, like bandwidth. I'm going to give you X, whether you do sequential or random or read or write, it's going to perform the same. But NAND, hard drives, all had varying performance. That's why those 4 numbers made sense.
Holistically, it starts with the HDDs, the spindle drives. The only impressive performance metric on a spinning, rotating platter was a sequential read, because fundamentally the mechanics basically. Needle can only be in one place.
At one time,
the rotor can only be in one. So you had to be in that track, or the performance just wasn't worth looking at. And then we started releasing NAND SSDs, and suddenly this awareness began to grow. Why is this so much faster? Because we had 10K platter drives that could achieve similar looking sequential speeds. The old Western Digital Raptors, what have you, could do over
I remember those. I remember
megabytes
rating
a second.
those,
With the old SATA 2 SSDs, it's about the same area, and yet the SATA SSD was so clearly faster and superior to that solution. So the awareness began to grow. Well, okay, not all the information on the computer lines up in these tracks, nice and neat. Sometimes we just need a little bit from over here and a little bit from over here, and we start to call that, random. You're looking for these tiny bits of information that are actually spread across the device, not linearly accessed. And storage technology, since then, it became increasingly obvious that that's actually represents more of the pain points for a lot of applications. They're getting stuck because they're waiting for the device to switch between these different address locations. So going back to what I said earlier about the word sentence chapter kind of thing, we can read that sentence, look to the next sentence, look to the next sentence. We can pull out all these little pieces of information very quickly, whereas in the NAND devices, they have to read that whole chapter, pull out a sentence, read the whole chapter, pull out a sentence, and that additional kind of processing is the lack of that additional processing is what gives us our advantage.
And just to add to that, right, all the NAND SSDs and all storage technologies today tend to quote their data sheet or any performance numbers at a queue depth. They say, okay, queue depth is basically the number of outstanding IOs which the host is waiting on for to process. And all NAND SSDs typically quoted at queue depth 32. 32, which is, I'll explain why it's more important.
So the queue depth is basically an outstanding list of requests from the host. And this goes back to HDDs. The idea was this platter, this needle, they're moving around all the time. How about we give you an address list, and if you happen to be passing any of these addresses along the way, it'll be more efficient if you stop and read them in that journey. So it was originally created as a way to try and get a little more performance out of these HDDs by making their read paths more efficient and write paths. But not much software, particularly in the client space, was ever adapted to take advantage of this. They continued to rely on the concept of, no, I want this right now.
Right.
And I'm not providing 32 things and, kind of give me what you can when you can. I want this in the order that I'm requesting it, one piece at a time.
And especially from a multitasking perspective, the developers are saying like, well, no, my app takes priority, not someone else's. But I mean, to kind of go along with what you were saying there, I think we can finally reference the two systems that you brought, these beautiful Aorus laptops here. What can you tell us about the performance numbers that we're seeing on the screens here between the two, and how does that relate to what you were talking about with like queue depth and?
So what we have here is one with 800p, which is the one system on your right, and the one with a competitive Gen 3x4 NAND. And we're just running IOmeter, right? A simple IOmeter run where we're measuring random performance at QDEP 1. And the reason QDEP 1 is important is we at Intel, we have a storage technology division which does a lot of research on what kind of usage and how people use their PCs and how storage is accessed. So we have data which says, pick any application, pick any benchmark. What we see is you need performance, high performance at low queue depth. And a storage device which is able to get that will benefit and give that responsiveness to the end user. It can go, the queue depth definition, it can go from benchmarks to applications to workloads. We in fact voluntarily asked permission to around 50 Intel employees. We traced their usage for over a span of 10 days, and that's the chart I'm kind of showing on the screen here. And what you see here is any kind of usage, you need these low queue depths. All of these accesses are happening at queue depth 1, 2, and 3, or 4 a little bit, and that's where you need that performance. And Optane just gets to that high performance starting at queue depth 1. NAND tends to need higher queue depths to kind of get to that performance. But what I'm also saying is that that's never realizable. because QDEP32 is never realizable in a client solution scenario. It's important for data center where they have a lot of logging and.
But a lot of this seems to be built on the immediacy of the request being fulfilled as quickly as possible.
What you were saying earlier about multitasking is basically you might have 4 applications asking for things at the same time, but they're all asking for one thing.
Right.
So that by definition becomes random because the data they're requesting is not related to the other data which is being requested. So again, that plays to why even though that stacks to potentially a queue depth of 4, none of those 4 are ever related. So all of these outdated metrics that focused on the biggest number you could extract from an HDD, which was just reading things in a straight line, they are outdated. They're archaic, so to speak. They don't represent anything that most of these applications are in fact doing.
What they're going to benefit from.
And what we're doing to change this is all our Optane SSDs and memory solutions will be quoting numbers at these low QDEPs. Quoting their numbers at QDEP 1, QDEP 2, QDEP 3.
So not apples to apples. A lot of competitors may be using QD32.
Got it.
Well, and have you found in the conversation that people are starting to adjust for this type of usage or this type of modeling, and in describing not just businesses and corporations, people that are running IT, but even just in the tech commentary space, people who review products are getting hip to.
It's absolutely catching on. You can see it deliberately cited in a lot of recent articles for reviewing these storage technologies. Maybe it's getting a little boring because the sequentials kind of stay the same and they don't really go anywhere, and they finally started to notice, okay, but we do notice in these workloads there is some difference.
There's
something must be accounting for that. So they're increasingly paying attention to this concept of the random performance at low Q depth.
Yep. And the other one which not just the random, the other thing which we're also very proud of with 800p is the consistency. Let's take an example of, I bought a brand new PC, everything works fast, everything's fun, right?
I love that.
Fresh out of the box, right?
Yeah.
Actually, I use that term all the time inside Intel. Fresh out of the box, everything's amazing, everything's running fine, all my benchmarks are scoring high, but I'm going to install an OS, I'm going to migrate all my data, I'm going to fill up my drive, and I'm going to start using it. And that's what we call steady state. That's where
ultimately you will achieve a steady state when it creates fragmentation. So it's similar to the HDDs. You remember you had to defrag all the time. It took hours. That was basically the HDD trying to identify as much as possible the operating system, trying to identify as much as possible. These files may be written together or read together. I should try and locate them in the same lane so that that can be accomplished more quickly. The problem with flash memory devices is that there is not a physical association. It's not like a address 0 to 1000 and everything's lined up in order. Right. The location of various pieces of information within that device is completely invisible to the operating system. It doesn't know. So it can't rearrange things to make them more efficient. What happens is, again, going back to the word page and word sentence chapter problem is when it's writing these little pieces of data, when the user just wants to write down a sentence, they all start to accumulate sort of in a random order as the SSD is creating these new chapters. And then when you go back to read them, you may want 2 related sentences that end up being in completely different chapters. And over time, that increases because the device doesn't really understand which piece of information is related to another piece of information. That all exists at the operating system or the host level. So the performance continually decreases over time as you add more and more information, and it becomes less and less contiguous.
And that's where, compared to Optane, you just have one straight line. Right, whether you use it on day 1 or the last day of the warranty period, whether you fill it 0 or fill it 100%, we have a consistent performance across usage, and that comes with the Optane technology.
Awesome. Well, gentlemen, thank you so much for demystifying Optane a little bit for us. Definitely. And now that everyone at home knows a little bit more about Optane, let's take a look at some of the specific Optane products that we have on that Newegg Now page today. Starting with the 800p Optane SSD, we have two different models available, 58 and 118 gigabytes, which seem like unorthodox sizes. So what are these products intended for, and what's the reasoning behind those specific sizes?
Yep. So 58 and 118, as I said earlier, this is a brand new memory technology, and though it has 64 GB of, the 58 has 64 GB of raw 3D crosspoint in it, and 118 has the raw 128 raw. Unlike NAND, Optane 3D crosspoint doesn't have spares. So when you do the raw from a conversion from raw media density to a logical density which is needed, the spare does give a benefit to the NAND technology, that's why you're able to achieve those 128 and 256, which are prevalent. With Optane, as with any SSD, there is a standard called IDEMA. It's a industry-wide standard which all SSD vendors have to meet. That's the amount of LBA capacity which is available to the end user. So hence, we start off at 64 raw, but we use some for our own memory management and firmware management, and the available density available for the end user is 58. So hence the 58 and 118 GB.
Very cool.
Good to know. Okay, so also on the Newegg Now page, we have the 900p Optane SSD, which we've actually featured on the show before. And when you buy that product today through Newegg Now, you can get a $30 Newegg gift card in addition. And so, what should people know, like the difference between the 800p and the 900p? What those two product lines? How do they differentiate?
900p is our fastest SSD. Period.
900p is the best. Do it.
Right, hands down. The 900p comes in a add-in card and a U.2 form factor, and it's high density, namely 280 GB and 480 GB. The 800p comes in a M.2, thus giving our customers and end user versatility to put it in mobile as well as desktop. If
smaller form factors.
Gotcha.
If you're buying in and you're trying to figure out whether you're buying an 800 or a 900, go for 900. Go buy the fastest one. And the 800p, we see it usage as someone who already has storage and looking for an upgrade. You could think of putting your OS, your system, on the boot drive. And your data drive could be your existing solutions.
But 900p, that's the system builder magic right there.
That's for desktops. Unfortunately, for mobile, 900p doesn't have a form factor which fits into mobile. So hence the 800p comes in the middle.
Right on.
Awesome.
All right. Well, thank you so much for joining us today, Avi and Mathew. You out there watching, make sure you check out the Optane products on newegg.com/newegg now.